So today we're going to look at graphs and functions and properties of graphs. And so I just put up a warm up for you guys to start on. So see how much you can do on this. And then we'll go over a problem that's similar to it after a few minutes. So I'll give you about 3 or 4 minutes to see how far you can get and do as much as you can. And then we'll talk about it. Okay, so you had a couple minutes to work on this. Hopefully you were able to do it. I am actually not going to do this problem. I'm going to have you guys turn this one in this afternoon as a in-class exercise for participation points. But if you didn't get that one, then maybe, if you didn't get it now, maybe you'll get it right after we talk about the next problem. So you might, I don't know if you want to take a picture real quick of that problem or not, or I guess I can come back and put that up during break time, remind me, so that you have it up there if you wanted to go back and look at it. Okay, so the next problem is almost identical, same sort of questions, different graph. I hope I did give a different graph. Yeah, I did, okay. Okay, so we're going to use a graph to answer the following questions. And so we have f of 0 is equal, and f of -6. So you need to be able to understand what they're asking for. So f of 0, all they're saying is, what is f of 0? What is your y value when x is 0? So if I go to x equals 0, and I go up here on the graph, my y value is 4. So another way of saying this is a point. And this would be the point 0, 4. So f of -6, we're looking at this and we're going and we're looking at the
0, 3.
Yeah, you are right.
Okay.
I'm just making sure you're awake. You are awake.
Not really.
Not really. Okay, you're right. So that is a 3. And f of -6, so let me look a little closer. F of -6, so when x is -6, our y value right here is -3. So f of -6 is equal to -3. And I guess they have the points listed there. So this is the point -6, -3 is another way to write that. F of 6, so go to the graph when x equals 6. So f of 6 is equal to 0. And then f of -4. So going to x equals -4 on the graph. If I come down here, oh, it didn't say f of -4. Yeah, it did. No, it didn't. I'm sorry, I skipped. It was f of 11 was next. F of 11. So f of 11 is equal to 1. So they want to know, is f of 3 positive or negative? So when x is equal to 3, is the point on the graph, is the y value on the graph going to be a positive number or a negative number?
Positive.
Yeah, so f equals 3. Up here, our y value is greater than 0. So f of 3 is bigger than 0. It's positive. And then f of -4, so if you look at f of -4 on the graph, would that one be positive or negative? So locate -4, and so our y value in this case is negative. So find all the values of x. So for what, I might need to read right. For what values of x is f of x equal to 0? So this is basically asking me, when is my y, what values of x make y equal to 0? And so another way to say that is we're looking for our x-intercepts. So if I go and I look at where my graph crossing the x-axis, there's multiple places. Right here, and right here. It could have just touched the x-axis and turned around, but in those cases it did not. So in that case, we have.
So they asked for the x-intercepts twice?
Yep. I guess so. If yep, so they did. So it's just another way of writing it and realizing what they're asking for. So for what values of f of x equals 0, so it would be when x equals -3, x equals 6, and x equals 10. And then it says for what values of f of x, or what values of x is f of x bigger than 0? So what that's telling me is it's asking me for what values of x is this graph above the x-axis, because it's strictly greater than 0. And so if I look at the portion of the graph where it's above the x-axis, I notice it's in here. Okay, so it wants the values of x in there. So let's look at it. So this value where it's starting right here, that was when x was -3. And then the value where it's ending, getting really, really close to, but not actually including, is 6. So there's different ways that we can write this. We can say that, in this case, that f of x is greater than 0 for values of x between. So inequality notation, -3 is less than x is less than 6. But a lot of times we'll be using interval notation. It will look kind of like it's a point, but it's not. We're starting at -3. All the x values from -3, not including, so we use that parentheses instead of a bracket, comma, and then a number we're ending at, which is 6. So this is the values of x.
Don't we have to do a union and go over to 10, 0?
Yay, thank you. We do. I didn't see that piece. Values. So you're right. So there's another place where it's bigger than 0, and it's bigger than 0 from 10 to 11. So just the y values, bigger than 10 and a little less than 11. And so let me just put that here too. So union 10 is less than x is less than 11. So interval notation sometimes looks like that could be a point, right? -3, 6 looks like it's written as a point, but it's not. Again, it's all the values, the range of values between -3, x values, and 6. Okay, so the next piece said, what is the domain of f? So let me just kind of erase what I put up here so we can see it. So domain, remember, are all your x values. Because this, this graph does not have arrows at the end, they're points. That's telling me that the graph is not extending further. And so we always go from smallest to largest. So the smallest x value that we have here is -6. And the largest x value that we have here is 11. So we're hitting all the values in here, again, between -6 and 11, but we're actually including those points. So our domain in interval notation is -6, but it has a bracket on that one side, comma 11. Or another way to state that is -6 is less than or equal to x, which is less than or equal to 11. Range is really the only time we're looking at y values when we're looking at the interval notation. And so range is all the y values that you're using in the graph. Well, because this graph is not extending further down here, the end behavior graph, and this is not going up further, I know that the smallest y value that I'm hitting on my graph is down here. And the largest y value that this graph hits looks at y equals 4, is up here. So all the y values, and there's no jumps in this graph, it's smooth and continuous, so I don't have to leave out any of these y values. And so my range is going to be all the y values, and always go from smallest to largest. What did I say that was? That was -3 is the y value there, all the way up to 4. Or we could have said this is -3 is less than or equal to, be careful, this is your y value, not your x value. Y is less than or equal to 4. So what are the x-intercepts? So like you said, we already kind of did that. That's the same thing as saying, what are all the values of x where f of x is 0? What are all the values of x which set your y value equal to 0? And those are your x-intercepts. I'm not going to write them down, but again, x equals -3, x equals 6, and x equals 10. And then the y-intercept, that is where your graph is crossing or touching the y-axis. And so this is where x is 0, y is 3. So it's a 0.03, or I can say y equals 3. So how often does a line y equals 1/2 intersect the graph? So y equals 1/2, that is a horizontal line. So let's just draw that line, the horizontal line, y equals 1/2. And so if I go in here and I have a horizontal line right here, this looks like 1/2. I'm just going to estimate it. So the number of places that this would touch or cross this graph, there's one right here, there's one right here, and there'll be one right here. So how often does a line cross y equals 1/2? It doesn't ask me where, it just asks me how many times, and it does it 3 times. And then how often does the line x equals 5 intersect the graph? Well, x equals 5, that is a vertical line going through 5. So if I go over here to 5, make a vertical line going through 5, it's only going to intersect this graph at one spot. So for what values of x does f of x equals 3? What values of x does f of x equals 3? So f of x equals 3 is another way of saying, again, your line y equals 3. So this is a horizontal line at y equals 3. And so if I look at this and I go through y equals 3, it's asking me for the x values. So if I look down at my x values, this is when x is 0. And it is when x is equal to 4. Those are the only values in there that give me And then last question, for what values of x does f of x equals -2? So same sort of question as M, the one above. We're looking at the horizontal line, y equals -2, and seeing how many times would that line intersect the graph and what are those y values. So y equals -2 down here. So I see that there's 2 spots. This is when x is -5. And this is when x was equal to 8. Okay, so hopefully that kind of clarified if you were struggling on that or you weren't clear on certain things. What you were missing and what you need to know. So questions over that problem? So we're actually going to kind of extend this more, and I might as well just talk about it right now. We're going to be looking at where's the graph increasing and decreasing or constant? So this is actually the next section, but again, this is just a good spot to do it, and I have the graph here. And we're going to cover it today anyways. And order doesn't matter in this case. Okay, so let's find the next piece. So let's call this O. Let's say find where f of x is increasing. Okay, so it's increasing. If I'm looking at the graph and I'm looking at where is it increasing or decreasing, I kind of imagine I imagine myself walking on the graph. Well, there's two different directions I could walk. I could either walk from left to right or right from left. When I think of it as we read left to right, at least in this country. So think of it as you're going to always walk left to right. So if you're walking left to right, are you going to be heading uphill or downhill? Well, from left to right, I notice I'm heading uphill until I hit my x value of 2. And so I start walking uphill when x is -6, and I stop when x is 2. I'm going to go back and look at that notation in a second, but we started at -6, and we're stopping when x equals 2. And I'm going to put a parentheses there. So we're hitting all the x values in there. And let's see, it looks like it's also increasing in another spot. Okay, I'm walking downhill, but I'm going to start walking uphill again once I get to my x value, which is 8. And I stop because of that point at 11. I'm not going to include those values because that's where I'm changing direction. The only reason why I included the -6 was because this was a closed point. Actually, I am going to include 11 because we stopped there. Okay, so what did I say? 8 to 11. So parentheses 8, 11 bracket. So where is it decreasing? So I'm thinking of walking. I would start walking here, going down until I hit y equals -2, but this, I want just the x values. And the x values are 2 to 8. Parentheses 2, comma 8. So they're also going to talk about, and then other sections that we're going to talk about today. So again, we might as well just talk about it. Looking at this graph, you should be able to find where your maximum and your minimum values are. Let me just erase it. So the maximum values, those are the peaks, and the minimum values that we call kind of the valleys. So it's also, max is the place where it's changing direction, where we start from going from increasing down to decreasing. And so we have a max value here when x is equal to 2. The thing is, when we say what the max value is, we actually say the y value. So here we have a max of 4 when x equals 2. This actually and not necessarily do all functions have it, but this function is on a closed interval. So this actually is our absolute max, because this y value is the highest y value that we can get on this graph. So we can say it's a local max, but it's also the absolute max of this piece or this graph. And then also, because of it's a closed interval, and I'll give you this theorem later, I can say that this is also a max because every value to the left of it is smaller and it's an endpoint. So I can say that we also have a local max. Again, it's the y value of 1 when x equals 11. And so minimum, so those are the smallest points. So changing directions from decreasing and then increasing, we would hit a minimum point. And so we have a min of, and so it's the y value of -2 at x equals 8.
What about the left side, the -3 at the beginning?
Left side, the -3. Well, x equals -3 right here, or you're saying x equals -6, y equals -3?
Yeah.
Yep, so you're right. So again, because this is a closed interval, we can look at our endpoints, and our endpoint can be a max or a min. And notice that this is a small. This is actually would be, because this y value is smaller than this y value, this would actually be our absolute minimum on this interval. So we have an absolute min.
So there's an absolute min and there's a min?
Yeah, so there's different kinds. And we'll talk about this, but an absolute min would be the smallest value that the graph hits. So this smallest y value the graph hits is -6. And they don't always occur, because if this graph had gone like this and shot downwards forever, it would never have a point where it stopped at the smallest. Okay. But there's a theorem that says if we take a continuous function and we make a closed interval, then there has to be on that interval, on that graph, there actually has to be an absolute max and an absolute min that occurs. And that could occur at an endpoint. And in this case, on this graph, it does occur at an endpoint. Okay. So that was at y equals an absolute min of -3, right? At x equals -6. And so I would call this min here, because it's not as small. This is just a local minimum on this interval between -6 and 11. Don't worry too much about it. We'll come back and we'll look more examples of this. But I just thought that this was a great place to show it while we had that graph right there.
Professor, did you say you were going to put the other one up during break?
Yes.
Okay.
So you can see it, and if you need to, you could always take a picture of it and come back to it. So we were talking about functions before. So remember, we were talking about functions, the certain condition had to hold. For every x value, it only gave us back in the domain. Every x value in the domain only gave us back one single y value. And so looking at a graph, we can see if a graph is a function by using our vertical line test. So what the vertical line test says is we can draw a vertical line anywhere on our graph, and it only intersects the graph at most once, then it's a function. And so basically, if I can show that I can draw a vertical line and it's going to intersect more than once, then I can say it's not a function. And so for instance, this value right here, when x is equal to 2, notice you're hitting 2 separate y values in here. And so this right here, by the vertical line test, is not a function. So following asked us to determine if the following is a function or not by using the vertical line test. In either case, use the graph to find the domain, range, intercepts, and any symmetry with respect to x, y-axis, and origin. Okay, so looking at this, I noticed that the first one is not a function. So let's just go through and say function or not a function. So first one is not a function. Going down this line, would you think that this 14, is that a function?
Yes.
Okay, so there's nowhere I can draw in here. That's a vertical line that would intersect more than once. And then what about 15? Is there any x value that would give you more than one y value?
It is a function.
Yep, so it is also a function. And then what about 16?
Function.
Function. What about, this would be 17.
Not a function.
Right, so there's a spot right here. If I can just show one vertical line would cross more than once, then it's not. What about this circle?
Not.
This piece, 19. So it looks like as x is approaching 0 on the right, the graph is heading down to negative infinity.
It is a function.
It is a function. Even though this is going to look kind of like a vertical line here, it is actually changing y values all the time. So this is. And 20?
Yes.
Yeah, okay. So pretty easy, right, to look and see if they're functions or not. It looks like all the rest are functions. Okay. So looking at this, now we can go through. It wants us to find the domain and the range and symmetry. Again, domain is all the x values you're using. And so I look at this first graph and I notice that I have all x values that are coming in from negative infinity, but then it's going to stop right here at this 1, and then, or negative 1, and then it starts again. Then the x value starts at positive 1, and it's going to go on forever to infinity. And so on my domain, if I was doing it in interval notation, is negative infinity. I hit the x value of negative 1. I put a bracket because it includes it. Union. And then I'm hitting 1, starting at 1 and including it. So bracket 1, comma, infinity. The range, though, that's again the only time we use the y values. Since this graph.
Question. Wow, I just forgot it. It's gonna pop up. I'll ask you again. Sorry.
Okay. So the range are all the y values. So notice this graph is shooting upwards. It's going to head that direction forever as x goes to infinity. So that's going to hit all our y values that are positive. And this piece of the graph shoots downwards forever. It's hitting all the y values going to negative infinity. Same thing on the other side of the graph.
I remember.
You remember your question? Okay.
Yes. So how do you know if it's including the points or not? So I can know to put a bracket or parentheses.
If the graph is going through it and it's continuing through that x value, then you're going to include it. Or if your X values, like, so number 15, we have closed points here. And so we're including those X values on those interval because it's closed. Where I think there was one like 19, the one below it. Notice that we have an open circle here. So we're getting really, really close to X equals 3, but we actually never include that value. So this is where you would use a parentheses.
Okay, thank you.
You're welcome. And so the range, we're hitting all our values from negative infinity to infinity. I don't want to go through all of these. So let me just choose a couple of them. What about symmetry on that one that we were just looking at, that first one? Is there any symmetry across x-axis, y-axis, or origin?
Which one?
The first one right here, this one that looks like.
That one should be symmetrical over the y-axis.
Okay, so it's symmetrical with the y-axis.
And the x would be over the origin, wouldn't it?
So it's actually symmetrical across all of them. If I folded the paper across that y-axis, it's a mirror image. If we folded it across that x-axis, it's a mirror image. And if we folded it in force, it's a mirror image. They lie on each other. So this is symmetrical. Yeeks. To x, y, axis, and origin. So what about, let's jump to maybe 22. Looks good. Okay, so 22, if we were looking at the domain, notice that you have that closed point here at -3. And so we have that x value we're including is -3, but that is the smallest x value that we get. So we have our domain is -3. But then notice that we hit all x values going on, going on, going on, and this shoots up forever. And so that's going to hit all the x values that are going to infinity. So our domain is the values from -3 including to infinity. I'm just going to write it like, or another way to say this, right? Inequality notation is x has to be greater than or equal to -3. The domain though, the range though, are all the y values that you're hitting. And so the smallest y value on this graph is at the x-axis. And so we're hitting the y value starting at 0. And then I notice I get up to here, y equals 2. But again, because this graph is going upwards forever, this is going to hit all my y values going up to positive infinity. So for my range, I can put it as bracket 0 to infinity. Another way to write this is y is greater than or equal to 0. So it doesn't look like this one is symmetrical. I can't fold it across the x-axis and get a mirror image. I can't fold it across the y-axis or the origin. So looking at this, let's take it a little bit step further. What about, where is this increasing? I'm looking at number 22. So if it's increasing again, walking, we would be walking uphill until we hit the x value gives us the direction 0. So we're starting from -3, it's a closed circle, so -3, all the way to x equals 0. Union, because we start walking uphill again when x equals 2. And then we continue uphill forever. So infinity. So again, it's always the x values you're using. And then the values where it's decreasing, well, it's decreasing starting at 0 and stopping at 2. This was pretty much all of 3.2 with some of 3.3 in there, starting to talk about increasing, decreasing. So basically just being able to look at a graph, be able to see if that graph is a function or not, and then to answer certain questions about that graph. So like this, how we got warm up. So being able to understand notation, what it's meaning, and looking at the graph and being able to evaluate it. So I'm going to jump into 3.3, and then I think we'll take a break after 3.3, or part after going over a little more of 3.3. Sorry. Okay, so 3.3 talks about, again, specifics about graphs. It looks at maximum and minimums. It also looks at, is a function even or odd? And so let's start there. So we actually know about even and odd functions without even knowing that we know about it. So an even function says the following. So a function is considered to be even if the following holds. If you plug in negative x wherever you see an x, so I'm going to write that as f of negative x, this is equal to your original function, f of x. Basically, it's saying if you have some value x here, you change the sign of that x, this would be f of x. You change that value of that x to be negative x, you're still getting that same y value. So even functions, notice, are symmetrical across the y-axis. So, note, even functions are symmetrical. Across the y-axis. Okay, so a function could be even, a function could be odd. So an odd function. And it's possible a function is neither even or odd. But if a function is odd, then the following has to hold. If we go back in and we plug in negative x wherever we see an x, so f of negative x, this would give us back the negative of our original function, f of x. So this is saying if I have some value x, this is my f of x value. I plug in the negative of my x, that would be me here, but it's going to spit back f of negative x. So it would be down here. Or sorry, negative f of x. Notice if I folded my paper across the x-axis and y-axis, this would be lying on top of each other. And so odd functions are actually symmetrical with the origin. So it might ask you, looking at a function or looking at an equation, is this function even, odd, or neither? So I always tend to start with plugging in negative x where I see an x, because that's part of my definition of an even function, and I use that as part of my definition as an odd function. So it's just, and it's easy then to see what I need to do. Let's see. Here's some problems. So if you had f of x is equal to 2x to the fourth minus x squared. And these questions are asking, determine algebraically whether each function is even, odd, or neither. So go back in, plug in negative x wherever you see an x. And would that give us back the original equation if we kind of manipulate it a little bit? So we have, this is equal to 2 all times, I see an x there, replace it with negative x. Raise that to the fourth power, minus, I see an x there, replace it with negative x. And then square it. Negative x times negative x times negative x times negative x. Multiplying a negative an even number of times make it sit positive, so we could rewrite this as x to the fourth. Minus, same side, sort of right reasoning there, negative x times negative x is positive x squared. So notice this is the exact same thing that we started with f of x. So since f of negative x equals f of x, this tells me that this is an even function. Okay, if it's even, it should not be odd or neither if it's a function.
So if it wasn't the same on this side, would it be an even function still or something else?
If it was not the same, then it's either neither or it would be odd. So if you plugged in negative x and you didn't get back the same thing that as this, then it's either neither or odd. Did that answer it, Kiara?
Yes, my bad.
Okay. What about capital F of x equals the cubed root of 4x? So if I plug in negative x wherever I see an x in that function, I'm going to see I have, this is equal to the cubed root of 4 times negative x. It's an odd root that I'm taking, so it's okay that there's a negative under here. We could, if we wanted to, we can break this down, and I'm just going to show it. So this is like the cubed root of -1. We can break this down times 4x. And I can pull out the cubed root of -1 is negative And then I'd be left with the cubed root of 4x. So notice this one does not look like my original. So it's not even. But if we look at now what is negative f of x, so that's just saying take our f of x function and multiply it by a -1 outside. So this is equal to -1 times the f of x function, which is the cubed root of 4x. So notice that's the same thing that we got when we plugged in -x wherever we saw an x. And this is equal to f of that -x. So since that's true, negative f of x is equal to f of -x, this is an odd function. So f of x, capital F of x, is an odd function. So again, probably most functions are not even or odd, but these would give us tools which are helpful when we're trying to graph. If we know it's an even function, remember we knew then that if xy was a point on the graph, then we also had a point -x, y. So basically, if we knew points, then we knew double the points. Same idea. If it's an odd function, if we know xy, and we know that if xy was a point on an odd function, well, when I plug in -x, I would get back -y. So this is also a point on the graph. So these are just kind of tools to help us with graphing in the future. And let me give you so we talked about where is the graph increasing, decreasing, and I didn't do constant, but we're going to look at constant. But let me give you the formal kind of way of writing it mathematically. So we say a function f is increasing on an interval I if for any choice of x of 1 and x of 2, so for any x of 1, comma, x of 2 contained in our interval I, we're going to put up the stipulation just so it's consistent that x of 1 is going to be smaller than x of 2. So with x of 1 less than x of 2, then the following must hold. Then f of x of 1, that y value, has to be less than f of x of 2. Okay, so it looks kind of scary, but it's not that bad. All it's saying is choose any x values, one smaller than the other, that were in the interval that we're looking at. It's saying that my y value, f of x of 1, has to be smaller than my y value up here at f of x of 2 if this is an increasing function. Could be increasing different ways, but if it's strictly increasing any value you chose in there, that y value on the left has to be smaller than that y value on the right to be increasing on an interval. It's said to be decreasing on this interval I. So decreasing, same stipulations. So if x of 1 is smaller than x of 2, x of 1 and x of 2 are contained in our interval, some I that we're looking at. Then if it's decreasing, that number on the right, or sorry, the left, has to be bigger than the number on the right. So then f of x of 1 is bigger than f of x of 2. So x of 1, x of 2, come interval, and it's decreasing. It's constant, meaning it's a horizontal line. Your y value is staying constant. If you can choose any values on that interval, x of 1, x of 2, and your y values are always the same. So f is constant. If again, x of 1, x of 2, contained in some interval I, and x of 1 is smaller than x of 2, then the y values are the same. F of x of 1 has to equal f of x of 2. Some x1, some x2. And this is f of x of 1, which is equal to f of x of 2. So we have some, pretend that's horizontal. You have a horizontal line. Okay, so those are the formal definitions of what it means to be increasing, decreasing, or constant on some interval I. If for some reason you could choose two values with those conditions in I, your x values, and those don't hold true for every x value in that interval, then it's not strictly increasing or decreasing particularly. Okay, so that probably, even though we're not done with that section, is probably a good spot to just take a break because we've been going for a while. Let me pause the video and I will move up the video, the screen to the in-class exercise you guys were working at the beginning of class. Like I said I would.
Can I ask a question really quick?
Yeah.
Can you show me on a graph the difference between a negative function of x and a function of negative x?
Negative function of x. What do you mean a negative function of x?
Well, we're going through if something is, if a function is odd or even, and we have a negative function of x is, if it's equal to a function of negative x, it's an odd function.
Okay, so basically, that's saying if I can plug in any negative value of x, so if you can plug in negative x for x, and it comes back where this is the same thing as your negative f of x. So this is giving us back the same y value, but except it's negative. And we get back the negative of y. then it's odd. So that one function where it was odd, I know what cubed root is. So cubed root, what was it, 4x? Any x value that I plug in, that's a part of our domain. So let's say I plugged in -1. If I plug in -1 here, I get 4 times -1, which is -4. I don't really know the cubed root. Let's plug in -2 because I know the cubed root of 8. So let's plug in -2 instead. So 4 times -2, this is -8. The cubed root of -8, it is -2. Because this is an odd function, this would be telling me that this point, another point on the graph, would have to be the opposite of this x value, which is +2, gives me back the opposite of my y value, which is 2, which is true. If I go back in here and I plug in +2 in here for x, 4 times 2 is 8, and the cubed root of 8 is +2. And so that's getting that reflection across this origin is what's happening. So any point I choose over here is going to be reflected down here is what it's saying to be odd. And your face is covered, Timothy, so I couldn't see your reaction if that was making sense or not.
It partially makes sense to me. I see how you're getting the reflection across the origin. Is f then, is function representative of the y-axis?
So f of x is just another way of saying the y value.
Okay.
The function
That makes sense.
g of x, h of x, if we have an equation with those are just representing y, the y value of your point. And it's just another way to write function notation. Oh, so I'm glad that you clarified that. So you guys are good. Are you good with that? That y is another way of writing y is just using the f of x. And so when we were looking at the things on the example at the beginning of class, when it said, you know, what is f of 2? That's saying, what is your y value when x equals 2? It's just a shorter way of saying those types of things.
Okay.
So great. And I thank you for asking that question. I'm glad I didn't turn off the video so it was captured and hopefully explained okay. Here we go. We stop the video for now. So we just looked at the graph earlier in the class and looked at absolute max, absolute mins, local max and local mins, but let me give you the formal definition. Now, hopefully I don't have problems. So, definition, let f be a function. So let f be a function. Defined on some interval I.
You did that to yourself. I know. So adorable. I made them all by myself too. Look at my computer.
Okay, just muted. So let f be defined on some interval I. Kind of sound familiar. And C be a number in I. And C is
What does that first word say?
Let. That's a funky L. So let f be a function defined on some interval I, and C is contained in that interval I. Then we say that a function f has a local max or maximum at C if there is an open interval containing C. So that the following holds: f of C is greater than or equal to f of x for all x in the subwit interval. Okay. The number f of C is called the local maximum value of f. So remember I was saying it's the y value we call as the local max or local min, and we say it's at this x value. So that's basically what it's saying. It says the number f of C is called the local maximum. Value of f. Okay, so we'll look at a picture. Let's say we had some graph. I don't like my graph. And so it's saying if you have some value C, C right here, looks like it's the highest value there. We can go in and we can put some interval. It doesn't have to be so big, but I'm going to make it, blow it up more to make it more prominent. We can put some interval around C, x equals C, such that all these y values in here, they're going to be smaller than or equal to this y value when x is C. So f of C here, all these y values would be this, well, this y value, right? This would be right here. This y value would be right here. And any number that you chose or any value of x you put in here would be smaller than this. So similarly, it's the same kind of idea for a local min. It's just that when we find this value C, it's going to be smaller than any other y value in our interval. So we say a function has a local minimum at x equals, let's say b in this case, if for every x contained in some interval I, and b is contained in I, f of b is smaller than or equal to f of x. So the number f of b is called the local minimum. Of the value x. Of the value of f.
What if we had a graph that looked like a mountain range? Could we have multiple local maxes and local minimums?
It's a good point. You're totally right. So we can have multiple max and mins. So we could have, So anything that is a peak, where you're changing direction from increasing to decreasing like this, coming up and increasing and then decreasing, is going to be a local max or a local min. So in this case, we would have a lot of these. So we could say that this is maybe, I'm just going to call them different variables, A and D. And so we would also have, so f of A is a local max. And f of D, the y value, is also a local max. So minimum, you can just, again, you can find some range about the C, or in this case, this X value, which is going to be, we said B. So if we dip down and come back, we could have multiple local mins. So in this case, at B, this is our f of B value. Says, okay, can we make some interval around B such that that B value, f of B value, is smaller than any other B value, right? So any other B, f of X value. So our Y values in here are always bigger than this f of B. And so by that, we say that there's a local min at f of B, or of f of B at B. So the only difference, let f be a function defined on some interval. We say if the number u in the interval I, for which f of u is greater than or equal to f of x for all x in the interval, then f has an absolute maximum at u, and the number f of u is the absolute maximum. Basically, it's saying if you have some point in here that is the largest y value that you're going to get on that whole interval, then that would, or graph, that would be the absolute max. If you have some y value on here, or that's the smallest, so like right here, notice that if I was looking at this for f of x, and I was trying to figure out where all my absolute max and absolute mins are, I don't know, I'm giving different letters of the alphabet, not in order. So I notice here we have an absolute, or we have a local min. F of B. And notice that E at x equals E, f of E is the smallest y value we would hit on this graph. And we have an absolute max, sorry, absolute min of f of E. And this is at x equals E.
So you can only ever have one absolute max and one absolute min, right?
Yes,
Okay.
but we could actually have an infinite number of
local mins and maxes.
Yeah. I'm actually thinking, because this says is equal to, I'm thinking that there could be multiple absolute maxes if they were all the same y values. I'm just thinking my trig function, y equals sine of x or cosine of x, because that's always hitting a max at of 1 and a min at -1, and it just oscillates back and forth, hitting those same values. So
I see that.
those actually are probably, we've considered absolute maxes because all of them are hitting those same values, and absolute mins. But the highest point would be the absolute max or absolute min in this case though, this graph does not have an absolute max or an absolute max because our graph is extending to positive infinity. Y is going to positive infinity as x goes to negative infinity, and it's shooting upwards. So in this case, this is a case does not have an absolute maxer. It does, though, have a local max. And that local max is going to be here at F prominent. So at F of F, F of F. Not at of. And so there's one theorem, and I kind of explained it to you. If your function is continuous and you're just looking at a closed interval for those absolute max or absolute mins or local max or local mins, it has to have those. And this is called the extreme value theorem. Okay, so if a function is continuous, on a closed interval, let's call that closed interval, we're starting when the x is a all the way to x equals b, then f has an absolute max and an absolute min. On that closed interval AB. Okay, so, and this can occur, or this could occur at an n value of the interval. So technically, we do not have the mathematical skills to prove that something is continuous. And that's something that one of the first things that you look at when you start calculus and proving something is continuous. Certain things have to hold true. But for us, basically, if you can draw your graph without lifting up your pencil, then that is a continuous function. And so it makes sense. If I draw some graph, it doesn't matter. And I just choose any interval A, B. So let's say this is A and this is B over here. So if I'm just looking at this piece of the graph, it has to have an absolute max and an absolute min. So here at my value of A, this is f of A. And then my other n value right here, B, this is f of B. So notice that there is a smallest value in here, and there's actually a largest value in here. And I see that here, this dip, maybe let's call this C. This is the smallest y value I have in here. So we would say f of c is an absolute min. The largest y value that I hit looks like it's f of a. That's the highest point. So f of a is an absolute max. On this interval AB, right? If I looked at that whole function from negative infinity to infinity, this does not have an absolute max or an absolute min because of the end behaviors of the graph. But closing an interval, I have now created it so it does have an absolute max and an absolute min. So we've already looked at this, the average rate of change between 2 points, but it's bringing it back into this section. So if we have the average rate of change between 2 points, and let's call them x is a, and then my y value I'm going to call f of a. And when x is b, I'm going to call my y value f of b. We can write it as follows. The average rate of change. I'm going to give you a little bit of different notation. This is the same thing as the change in your y value. So it's a triangle with a y all over the change in your x value. And you can write that with that triangle and then the x. Okay, so if we do this, our change in our y value, this is f of b minus f of a, all over the change in our x values. We started with b for our y value, so b minus a. Okay, so we have to put a little bit of a stipulation because b cannot equal a. And then we talked about it already too, was the secant line. So the secant line is the line that joins those two. So basically, if you have a graph, you have some value A, we have some value B. So f of B, f of A. You're looking at the line in between joining those two. Thought maybe this might be helpful. Maybe not. Okay. If I join these 2 points, pretend those would join each other. The average rate of change would be the slope between here. And this line that joins those 2 points, pretend those do, that is called the secant line. So the secant line is the equation of the line with the slope of the line between AF of A and BF of B. And passes through those points. Okay. Okay, so I did an example of that before. I just want to get through, darn it, I'm already behind. I want to jump into looking at the time, 3.4 really quick. 3.4 gives us functions that we should know how to graph, basic functions. And so you should be familiar with the following shapes of graphs. Just do this. So you should be familiar with the constant function. Basically, if you had an equation that was just equal to a constant, you should know what that looks like. So this would be in the form of f of x equals to k. So technically, if we look at the graph of that, that is where k is equal to a constant. So some number. So this would be horizontal line through y equals k. You should know your identity function. I actually didn't know it was called this. F of x is equal to x. Basically, for every x you plug in, right, you get the same value for y. And if we graphed y equals x, we get this diagonal line. You have your square function. So this would be f of x equals x squared. You should know that that graph looks like a parabola, and it's centered at the origin. Guess what's the next one? The cubic function, or cube function. If we looked at the cube function, this is f of x equals x cubed. And so if I graph that, the following shape kind of looks like this. And you can get all of these by just simply just going in and plotting points and seeing what the shape looks like. We got the square root function. So the square root function is f of x equals square root of x. So when x is 0, you got 0. It's kind of a half sideways parabola looking shape. The cube root function. And so this one is f of x equals the cubed root of x. And the shape of this one. Similar to x cubed, but it's flatter, kind of more like an S shape. The reciprocal function, we're almost done. So this is f of x equals 1 over x. If we graph this one, we have in the first quadrant, looks like this. The second or third quadrant, it's like a mirror image, so it's actually a odd function. So it looks like this. So we have asymptotes, a vertical asymptote, and we have a horizontal asymptote, and we'll talk about that more later in this course. This is y equals 1 over x. Notice x can't be 0. You have the absolute value function. I think that's the last one. So f of x equals the absolute value of x. So that looks like a V. Symmetrical with a y-axis. Okay, so darn it. The last piece in this section is piecewise functions. And so that's where you basically have different pieces of equations. You have different equations, and for each equation, it's defined for different x values. So I'm just going to do one really quick. And then we'll look at it more next week, but just to get an idea, and maybe you can get further on the homework. So if you have an equation negative x plus 1, it's telling me that this is for if x is between negative 2, including, so negative 2 is less than or equal to x is less than 0. Tells me I have the equation y equals 2 if x equals 0. And I'm going to use the equation x plus 1 if x is between 0, so 0 is less than x, and less than or equal to 2. Okay, so I have, basically, I'm only looking at things between negative 2 and 2, and I have 3 separate graphs that's going on for this, but tying them together. And so if you're just looking at from x being from negative 2 to 0, we would use this equation. Oops. So let me just plug in negative 2 there. I know if I plug in negative 2 there, which is part of this equation, negative of negative 2 is 3 plus, I'm sorry, negative of negative 2 is 2 plus 1 is 3. This is a solid circle because of the equal sign. And then I know this is a linear line. My slope is decreasing. It's negative 1. So go down 1 over 1. And I'm going to do that until I get to 0. So when x is 0, my y value would be 1 there. The thing is that this does not include, it's strictly less than. And so open circle at 0. So when x equals 0, you're only looking at one thing. When x is 0, we're going to put in 2. So basically, this is just saying we have a point, right? At x is 0, y is 2. So a point right here. And then the last one says, let's graph x plus 1, but we're only doing it between 0 and 2. So let me even put in 0 there, even though it's not included. So you really actually want to put in the in values of your inequality and just determine, is that in value of your inequality on that piece of the graph going to be an open or circle or closed circle. So when x is 0, I get it 1 back. But that is open circle because it's not included. So notice that's the same place as right here. And then when x is 2, I know this is a line. So if I plug in 2 here, 2 plus 1 is 3. Okay. Notice how I didn't extend my graph past these values because it's not part of the equation. So my domain really is between -2 and 2. So I just wanted to do a quick example of that. I did not get as far as I wanted today. So for homework wise, you probably can do a lot of 3.4, but I will lecture a little more on that next week. So that homework won't be due. But don't leave yet. Don't turn off your videos.